Okay, so yesterday we slaved over a hot chain rule in order to recover this formula here. So what we're trying to do is find the wave functions that represent the states of well-defined orbital angular momentum. And I explained what the strategy was for doing that, and that strategy involved knowing what these operators are as differential operators in the position representation, and some rather tedious chain rule work was required in order to extract this formula here, and I finished with a triumphal acquisition of this formula here, and I merely stated that this was what you got if you pursued the line of argument for find L minus. Okay, so we're now in a position to find these wave functions. Let's call it psi Lm. This will be some function of r, theta, and phi, because we're looking at this in spherical polar coordinates. So this, of course, is r, theta, and phi Lm. Now, the radial dependence of this wave function is going to be completely unspecified, because we're only going to require, all we're going to require is that Lz on Lm is equal to m Lm. It's an this thing has got to be an eigenfunction of this operator with the eigenvalue m, which we now know to be an integer. And we are going to require, similarly, that L squared on Lm is equal to L plus 1 of Lm. We're not going to direct, and we will find, we haven't yet calculated this operator, as this, what L squared looks like as a differential operator. We will get to that. But it will also turn out to involve only derivatives with respect to theta and phi. So these operators, none of them involve anything about radius, and so this function is an arbitrary function of radius, and all we're going to be able to discover is what its angular dependence is by imposing these requirements here. Okay, so what can we say? We can say, first of all, this equation is going to imply, put into the position representation, it says that minus I d by d phi of psi is equal to m of psi, which we, of course, immediately recognize as telling us that psi at r, theta, and phi is equal to e to the I m phi times psi at r, theta, and nothing, if you see what I mean. And nothing, and nothing, and nothing. So there's some kind of a constant here, right? This thing doesn't depend on phi. If you differentiate this with respect to phi, you bring down an im. The i's make another minus sign that cancels this, and you end up with m times whatever it is. So what we know is, this should have its subscripts, I suppose. So what we know is that psi Lm is equal to some function of r and theta times e to the I m phi. I guess we kind of already knew that. Now we're going to, oops, and we are going to, well, yeah. We're now going to impose the condition that L plus on psi LL is equal to naught, because this operator would create a state in which m, we've put here the value of m equal to L, which is its largest value. This would try and make m even bigger than L. We know that's not possible, so we have this equals 0. So copying down what that is, turning this equation into the position representation, e to the I phi, sorry, e to the I phi, d by d theta plus I cotangent theta d by d phi, operating on e to the I L phi times this function k, which depends on r and theta. Especially it depends on theta. The r dependence we don't care about because we've got no differential operators here with respect to r. So this term looks only at that and brings down an IL, right? So what's that? Sorry, this has got to equal 0. So we get two terms. We're going to, this d by d theta term looks only at that. So we discover that decay by d theta minus cot theta, L cot theta, we're bringing down an IL, K equals naught. Then there's a factor of e to the something or other phi, which we can cancel away. It's not interesting. So here we have, this is a linear first order differential equation, the friendliest kind of differential equation. So we solve it with an integrating factor. The integrating factor is e to the integral of this here, e to the integral of minus L cot theta d theta. But I think that the integral of cot theta d theta is log sine theta. So this becomes e to the minus L log sine theta, or e to the log of sine to the minus L theta, or simply sine to the minus L theta. That is the integrating factor of this equation. In other words, the equation states that d by d theta of the integrating factor, which is sine to the minus L theta times the function, is equal to naught. In other words, this thing is equal to a constant. In other words, k is equal to a constant, which is obviously going to be some kind of normalizing constant, times sine to the L theta. And we have discovered this constant in principle depends on r, right? It's allowed to, you can have any r dependence you like. So what we've discovered is that psi LL is any function of r you like times sine to the L theta e to the I L phi. This is an important kind of result. And now we're in a position to calculate anything else, because if we want to find what psi L minus 1 is, then it's equal to L minus divided by an appropriate normalization factor, which happens to be L plus 1 minus L minus 1. Remember, these ladder operators come with square rooty normalizing factors. That was the case in the harmonic oscillator. That's the case also with the angular momentum operators operating on psi LL, which we now know what it is. We now know that it's sine to the L theta e to the I L phi times the unspecified function of radius. And this L minus, let's roughly speaking put in what it is. No, maybe we do it on the next board because we want to be able to see. We want to be able to see those magic formulae, right? There they are. This tells me that psi LL minus 1 is equal to, I think this is just a square root of 2L. So it's function of radius over the square root of 2L, all being well, times e to the minus I phi times, there's probably an overall minus sign coming from that formula at the top there, d by d theta minus I cot theta d by d phi, working on the function we first thought of, which is sine to the L theta e to the I L phi. And what are we going to get? This d by d phi will again bring down, you know, an L, etc. And then this exponential will take 1 off that, so we'll end up with something that goes like e to the I L minus 1 phi. This will differentiate sine to the L and produce L sine to the L minus 1 times a cosine. This cotangent, multiplying that, because this is cos over sine, will again produce me a cos times sine to the L minus 1. So the whole thing is going to be minus unspecified function of radius over the square root of 2L times, there's going to be everything's going to go like e to the minus I L minus 1 phi. And then from here, we're going to get an L. From here, differentiating that, we're going to get an L. Well, there's going to be a factor, sorry, of sine to the L minus 1 theta cos theta. And how many of them? From here, we'll have an L And from here, we're going to bring down an L, well, an IL. They will cancel, so I think it'll be plus another L of the same stuff. So you see that we have something like the square minus the square root of L over 2, whatever your unspecified function of radius was, e to the minus I, L minus 1 phi, times sine L minus 1 cosine theta. And we could now apply L minus to this again and get the next in sequence, right? We're not going to do it because life gets very boring. L minus 2, but it's just a matter of differentiating. But the thing to pick up is that when we do this next, when we differentiate this thing is going to become more complicated because we're going to be doing a derivative of this with respect to theta. So we will get a term that goes like sine to the L minus 2 times cos squared, and then differentiating this, we'll get our sine to the L back. So we'll get two different terms. And then when we differentiate again to get psi, so this is going to be an amount of, it's going to be amount of sine L minus 2 times cosine squared. Differentiating this, we'll get L minus sine to the L minus 2, and then we'll get a cosine which goes onto that. And we will also have, from differentiating this, plus an amount, call it B, of sine to the L theta. So there'll be two terms, and it'll all be times e to the minus L minus 2 phi. And when we differentiate this again, in order to get psi L minus 2, it'll get more Byzantine because this will generate me an L sine to the L minus 3 times cos cubed. This will get back what we had here and so on and so forth. You get more terms. You get a longer thing coming in front of the exponential. So what do these things actually turning out to be? It turns out that what this is a normalizing constant times PLM of cos theta times e to the minus, make that LM. If we just keep going, this will turn out to be a normalizing constant times the associated Legendre function PLM of cos theta times e to the minus, sorry, that's an I, not a minus, isn't it? Yeah. This should have been a plus. E to the I m phi. So this thing, I think you may have met this, right, in Professor Essler's lectures. This is an associated Legendre function, probably derived from solution in series by using Frobenius's method. I'm not sure. Is that right? But fundamentally, I don't think this is very helpful knowing this is an associated Legendre function. I think it's much more helpful knowing how to do it this way. The normalization factors take care of themselves if we put in these square root animals. And we start with this thing correctly normalized. How do we normalize this traditionally? What we do is we say psi Lm is equal to some function of radius to be discussed times y Lm of theta, where this thing, the spherical harmonic, the spherical harmonic is a multiple of PLM times e to the I m phi, normalized so that if you integrate d theta sine theta d phi over the sphere of YLM mod squared, you get precisely 1. So the YLMs are correctly normalized, so if you mod square them and integrate them over the sphere, they come to 1. The PLMs have a daft normalization. And that's why I don't think you should bother with PLMs. They're just stupid functions. Historically, they've been defined in a bad way. The YLM's the things to go on, but the YLM is actually one of these functions of cos theta times e to the I m phi. So it has a very simple phi dependence, this animal here. And we need to so now let's just summarize what we have. So these things, YLM, theta and phi, are the wave functions, essentially. They're the wave functions theta phi Lm. They're the wave functions belonging to states of well-defined orbital angular momentum. That is to say, if in the position representation you apply, Lz to YLM, Lm, you get m times YLM, which is a trivial result because this thing goes like e to the Im phi. And if you apply L squared to YLM, you get L plus 1 of YLM. So, if you have an electron, here's the nucleus, if you have an electron in orbit around the nucleus, it seems reasonable to say that it's reasonable to ask, what does this system look like? What does the wave function of the electron look like if the electron has well-defined orbital angular momentum? The answer is that its wave function is going to be a function of r, which we'll see, will tell you how much it's oscillating in radius as it goes round and round, times one of these YLM things. So these YLM things should give us, we should be able to understand them in terms of orbits at some level, right? So let's address ourselves to that. What can we understand about these mathematical functions YLM in terms of what we understand intuitively about how an electron should go in an orbit around its nucleus? So the place to start is when L is large, because when L is large is when we're sort of approaching the classical regime for which we have some grip. And the pictures at the top here are these are contour maps of the real part of YLM. So YLM is an inherently complex thing, right? YLM consists essentially of PLM, some real function of cos theta, times e to the Im phi. So by focusing on the real part of that complex function, we've got that PLM times cos m phi. And these ones at the top are all for L equals 15. This is for m equals 15. This is for some intermediate one, m equals 7, and this is for m equals 2. So what's the physical what's the physical interpretation of these? This thing, and YLM is a function on the sphere, right? It assigns a complex number to each point on the sphere. So the real part is a real number on the sphere, and what's being plotted here are contours of constant value of this real number on the sphere. So you have to imagine that these are pictures of spheres. So what do we see here is that around the equator we have, so dotted contours mean negative values of the real part, and full contours mean positive values of the real part. So the large values of the real part are around the equator here, and that's apparent from this maths because we know that this is YLL for L equals 15, so in fact it's sine to the 15 theta e to the 15 I phi, right? That's what this thing here is. And if sine theta is 1 on the equator and less than 1 everywhere else, if you take a number that's less than 1 and raise it to the 15th power, you have quite a small number. So you were expecting that the number gets small quickly as we go away from the equator. That's exactly what we expect on physical grounds because the state L equals 15, m equals 15 means you've got 15 units of angular momentum, broadly speaking, and they're all of them parallel to the z-axis. So this thing is an electron that's orbiting with in a plane. Classically, it'd be orbiting in a plane, the equatorial plane that was perpendicular to the z-axis. So where do you expect to find the particle? You expect to find the particle in the equator and nowhere else. Where does the wave function peak in amplitude? In the equator and nowhere else. Why is it segmented like this, like an orange, right? we have sort of waves going around the equator here. It's big, small, big, small, big, small. That makes perfect sense because the change in because P, the momentum is minus I h bar d by b position, right? So if you have something with a large momentum, it's to do with a large gradient, a large rate of change of the wave function. Now, the amplitude of the wave function does not change 1 iota as you go around the equator, because this thing has amplitude which is sine to the 15th power of theta, so it's completely constant at 1 around the equator. But the phase of this wave function is changing like crazy as you go around the equator, because it's e to the 15I phi. And that is expressing the fact, according to this, that the momentum of the particle is directed tangentially around the equator. It's rushing around the equator. It's in the equator and it's rushing around the equator. What else would you expect? That's exactly what should be the case. So let's go now to this case, which is, oops, I've lost it. M equals, the extreme right one, m equals 2. So we've still got L equals 15, but we have m equals 2. So we've got a particle which has 15 units of angular momentum, but only 2 of them are parallel to the z-axis. So classically, what this amounts to is that here's our sort of notional sphere, and you'd think that the orbital plane classically would be tilted like this, well, even more so, sort of like this-ish, very highly inclined, so that the spin axis of the orbit was pointing almost in the xy plane. So what we're expecting is that the motion is mostly from the northern hemisphere down into the southern hemisphere and back up again. So we expect the contours on which the phase of the wave function changes rapidly. Oh, fiddlesticks this. So annoying. The direction in which the phase varies should be from north to south, and lo and behold, it is, right? So so now we have, instead of having an orange peel plan, we have sort of rings going around on which the phase is. So and if indeed we put m equal to 0, we would have a wave function which had no variation as you went around the sphere. It would all be variation as you go from the northern hemisphere to the southern hemisphere, which corresponds to the fact that the particle is moving this way. Now, this particle has most of its angular momentum in the xy plane, but the thing is because we know the angular momentum in the z direction, and Lz does not commute with Lx, we do not know how much angular momentum it has in the x direction. Most of its angular momentum is in the x and y directions, but we don't know whether it's positive or negative. So that means that we cannot, in this picture, see an orbital plane. The probability of finding the particle is sort of large all the way down here and all the way down there. And if m was 0 and the angular momentum vector were exactly in the xy plane, we would have absolutely no variation in probability to find the particle as we went around and around the sphere. Well, in fact, even now we have no probability to go around and around the sphere. The real part. So what this thing is, it's a function of theta times e to the I 2 phi. So the phase is varying as we go around the sphere, but in fact the amplitude is not varying as we go around the sphere. The amplitude to find the particle is constant as you go around the sphere on small circles. And that is associated with the fact that we do not know, we are not allowed to know, it is forbidden to us to know which way this angular momentum vector is pointing. But where are we most likely to find the particle? Are we likely to find the particle most likely in a given patch on the equator, or most likely to find it on the pole? Well, this wave function is largest at the poles, the North Pole and the South Pole, because it's going around, this particle is going around almost over the poles in a plane which is of unknown orientation. So there's great uncertainty. There are many places where it could cross the equator, but what we are sure of is it goes close to the pole. So that's why the probability, there's a sort of crowding of imagine a bunch of circles for a polar orbit going around the sphere at different orientations, they'd all pass through the pole, and there'd be a great crowding of the circles near the pole, and that generates the high amplitude to find the particle at the pole, a relatively low amplitude to find it at the equator, but not a vanishing amplitude to find the equator, because it does cross the equator twice in each cycle. So this amazingly, this is an intermediate case, m equals 7, L equals 15. This curious mess of squares in which you can see the real part is alternately positive and negative, the contours are dotted and full. This represents the situation where the orbital plane, in classical physics, the orbital plane would be just moderately inclined at 45 degrees or 30 degrees or something to the equator, and there is absolutely no orbital plane visible there. And this is where we come to a key point, that if you want an orbital plane to be visible, and after all, the orbital plane of the Earth is entirely visible, and the Earth presumably moves according to these principles too, we have to have, how do we get an orbital plane to emerge? The way we get an orbital plane to emerge is by quantum interference between many states that look rather like this and have a patchwork of pluses and minuses. If you have several of those patchworks of pluses and minuses, you can get the amplitude to cancel most places except in some inclined orbital plane. So it's uncertainty in the angular momentum which will generate for you, if you want it, some degree of certainty in the location of the orbit going around the sphere. It's the old uncertainty principle over again. So those are the classical, this is almost the classical regime up here, right? Of course, as the Earth goes around the sun, its angular momentum is, who knows, 10 to the 50 h-bar or something, right? It's simply, I haven't worked it out, it's some staggering number. So you would have to imagine 10 to the 50 little patches here of pluses and minuses, or maybe it's 10 to the 50 squared, I think it probably is, 10 to the 100 patches of pluses and minuses, and then you can, by taking a number of those, maybe you take 10 to the 34 of those with 10 to the 50 patches, you'll be able to arrange for the pixels to cancel everywhere except in some extremely narrow band, which is the inclined orbital plane of the Earth. So atoms don't live in that regime up there of L equals 15. Atoms live in this regime, this Tarsum regime down here. This is, where am I? This is L equals, I've lost it. This is L equals 1. And these are the three things for L equals 2. So this is y1, 1. So that means you've got 1 unit of angular momentum, and, well, it doesn't actually, right? Because what does L equals 1 mean? L equals 1 means that L squared has answer 1, 1 plus 1 equals 2. So the total angular momentum, the square root of L squared, has answer root 2, which is distinctly bigger than 1. So we've got as much angular momentum along the z-axis in this 1-1 case as we can, which means the particle definitely is going around the equator. So you can see that it's going around the equator. Well, I can't from this angle, but I hope you can, in the sense that the thing isn't constant. The wave function has gradient. As you go around the equator, there's a gradient. On the other hand, there is not a very high probability of finding it in this is only the real part of the wave function. If we would look at the imaginary part of the wave function, well, how does this one goes like sine theta, not like sine to the 15th theta. This function here is sine theta times e to the I phi. So as you go away from the equatorial plane, the amplitude to find the particle falls, but only falls like sine theta, so it's really quite likely not to be in the equatorial plane. And that's associated with the fact that though we've done our best to get the angular momentum along the z-axis, it isn't along the z-axis because its total angular momentum is 1.4 something times h bar, and only one of those units is along the z-axis. So it's in some sense inevitably inclined. And this is the case when we have no angular momentum along the z-axis. So this is the case of polar orbits. The amplitude to find the particle is greatest at the two poles, smallest at the equator, etc., etc., etc. But the whole picture is less clear-cut. And I won't bore you by talking about these, but it's worth thinking about the L equals 2 case to see to what extent you can make sense of these, physical sense of these pictures here. Okay, so now we should address an important topic, which is the parity. This is practically an important topic, the parity of YLM. So remember the parity operator, P, working on a psi, makes a state whose amplitude to be at x is the amplitude to be at minus x if you were in the state of psi. That's the definition of the parity operator. And these states of well-defined angular momentum turns out have well-defined parity. That's what we're about to show. And what's more, the parity is -1 to the L. So states of different angular momentum have alternating parity. Some are even parity, some are odd parity. That's what we want to show. Okay. So as what we do now is, so this is sort of imagined in Cartesian coordinates. We need, since our y's are all defined in terms of polar coordinates, we need to translate the operation of going from x to minus x into spherical polar coordinates. So as we go from x to minus x, it's easy to check that what happens is that theta goes to pi minus theta, and phi goes to phi plus pi. So this reflection action, you need a picture really. Well, we can just about show it, I suppose. I hate three-dimensional pictures because it's a three-dimensional picture. Okay, here's theta, the spherical polar coordinate theta, and what we have to do is take this point and move it down here, right? And what we do is we move this point down to here. That's the theta goes to, so theta, this theta goes to pi minus theta. And then, having got it down here, we rotate it through, out of the board and back into the board, through pi and phi, and that's how we get it down here. So these are the changes in polar coordinates that are associated with that. Now, YLL, oh yeah, well, what else can we say? So theta goes to pi minus theta, what does that have to say about sine theta? Sine theta goes to sine pi minus theta. And sine pi minus theta, it's easy to check from a variety of arguments, is actually equal to sine theta. So sine theta doesn't change, and e to the I L phi, what happens if you add pi to e to the I L phi? Well, you're adding e to the I, you're getting an extra factor, e to the I L pi, which is -1 to the L times e to the I L phi. Is that right? Okay, now, YLL is a constant, rather a yucky constant, so I won't bore you with it, times sine, we've proved this, sine to the L theta, e to the I L phi. So this thing does not change sign, or it doesn't change at all, right? So we can say now that YLL goes to, this doesn't change sign, it doesn't change at all, and this one changes sign. So it goes to -1 to the L of YLL. That's under x goes to minus x. So this means the parity of YLL is even if L is even and odd otherwise. That's a very important result, and moreover it generalizes because we have that YL minus 1 is L minus over some square root that's really boring. Well, it turned out to be 2L, so we may as well put it in, times YLL. And what about this? What's L minus? L minus is Lx minus ILy. In the position representation, what is this? This is minus I h bar of y d by dz minus z d by dy plus, minus, who knows, h bar. It doesn't much matter. The key thing is that we're going to have here as z d by dx minus x d by dz. And when we change x to minus x, y to minus y, and z to minus z, these things, we get change of sign here and a change of sign here, change of sign here, change of sign there. So L minus, and also, as a matter of fact, L plus is unchanged by P. The strict mathematical statement is that the parity operator commutes with either of these animals. Indeed, all the angular momentum operators commute with the parity operator, basically because they contain products of positions, or if you like, ratios of positions, whatever. They don't change. So what that means is that this is going to have the same parity as this, because if you apply the parity operator to this, you're applying the parity operator to this, those can swap in order. This turns to minus itself. The minus sign can be taken out, and therefore we've shown that leads to the conclusion that this thing has the same parity as this. Let me just write that argument down, perhaps. So we have that P on y L minus 1 is equal to P L minus psi, not psi, y L over some square root, that's not interesting, is equal to L minus P y L over the square root, which is equal to minus 1 to the L times P times, this thing produces YLL. So we have L minus YLL over the square root. But this is YL minus 1. So it's equal to minus 1 to the L of YL minus 1. So we conclude that LM has parity minus 1 to the L for all M. This is a very important fact because it enables you to set to 0 all sorts of integrals which would otherwise be very tiresome to work out. How are we doing? Yeah, I realized that there's one other thing, so which we've unfortunately lost. Is it coming back? No. What I wanted to do was show you the forms of the YLMs. The first few, you need to have some sense of how they go, right? So y nothing nothing is 1 over the square root of 4 pi. Y, which order they put in? Yeah, so we want y1 nothing is basically cos theta. There happens to be some factor of root 3 over 4 pi. Y11 is, of course, sine theta times some normalizing factor e to the I phi. And y1 minus 1 would be the same thing with a minus sign here. So the point is that the y1s go like cos theta and sine theta. And the y2s go like cos theta, sine theta. So y2 nothing is equal to a normalizing factor that happens to be 5 over 16 pi. That's not so interesting, times 3 cos squared theta minus 1. And y2, 1 is minus the square root of 15 over 32 pi, which is not so 32 pi, which is not so interesting. What's important is it goes like sine 2 theta, which can also be written as sine theta cos theta, and the other one goes like, of course, sine squared theta. This one has e to the 2I e to the I phi, and this has e to the 2 I phi. So what do we need to remember? What we need to remember is that obviously y00 has no angular dependence. Yes, okay, so I think the machine has finally come back to life, and the correct formulae are here. That's what I wanted to show you. The y1s have a cos or a sine. The y2s have a whiff, well, that you can either think of, they have a strong whiff of cos 2 theta and sine 2 theta, right? Because cos squared theta is something like a half of 1 plus cos 2 theta. So there's a whiff of, this could be rearranged to involve cos 2 theta. Here we have a sine 2 theta, and this sine squared has a whiff of cos 2 theta about it because we know that sine squared theta is a half of 1 minus cos squared of cos 2 theta. Something like that, right? So we have these double angle formulae, and so it would go on. If we were looking at y3, would have these things would have dependencies that look like cos 3 theta and sine 3 theta, right? That's the pattern. But you don't need to know about the pattern beyond here, but these patterns you're expected to be able to sense, so that when you're given a function of theta, which is made up, a linear combination of these things, you need to be able to unscramble it and write it as the right linear combination of those y's. Right. The next topic. So in preparation for work on atoms, we need to get an important formula for how kinetic energy can be expressed in terms of L squared, and this finally obliges us to face up to the tedium of calculating what L squared is, what differential operator represents L squared in the position representation, right? So we start by observing that L squared it can be written as L, which way around do I want to write it? Yeah, plus minus. Okay, I want to write it, I can write it either way, but I'm going to do it consistently like this. Well, let's see what we're going to have to add to this to make L squared. This is Lx plus I Ly, Lx minus I Ly. What's that going to come to? That's going to come to Lx squared plus Ly squared plus, well, minus I Lx comma Ly commutator. That's what this thing multiplies up to. If we want to get L squared, we'd better add, here's a good start on L squared. Let's add Lz squared. But we need to get rid of this. Lx comma Ly is I Lz. So we've got here, what with this minus sign, a plus Lz. We'd better take an Lz away in order to square the books. So that's what this should be. Sorry, this should be put equal to plus Lz squared minus Lz. So that's that. So what we do now is we write down L plus L minus, which we have floating up there in the stratosphere. So we have that L squared is equal to e to the I phi d by d theta plus I cotangent theta d by d phi. And that should operate on L minus, which is minus, I'll take the minus inside the bracket, e to the minus I phi d by d phi, d theta, sorry. This minus sign was up there outside the bracket, I think, plus, because I propagated the minus inside the bracket, I cotangent theta d by d phi. So this disgusting mess is that product. And then we have to add Lz squared and take away Lz. This thing is minus, Lz is minus I d by d phi. So with that minus sign, we get a plus I d by d phi. And this is going to be minus d2 by d phi squared. So the name of the game is to differentiate out this piggy mess and find out what it simplifies to. Some parts of it are easy, right? We're going to have, for example, at the end of the day, we will have terms where this is multiplying this, and this is multiplying this, and these two exponentials have killed each other off. So we will have a term like d2 by d theta squared. These i's will generate, sorry, there'll be a minus d2 by d theta minus, because one of these has got a minus sign. These two will create me a minus cot squared d2 by d phi squared. That's the easy part. Right, now the mess. There's going to be some mess because this differential operator is going to bang into that, okay, and generate a minus I times what will kill this off. So we'll have a minus I, oops, oh no, but then it's times this, so the minus I that we're getting from here will meet this and generate a plus 1. So we have cotangent theta, that's this cotangent theta times this bracket. So that's the result of this differential operator seeing this. When this differential operator sees this bracket, all we get, we get a mixed derivative term. We get two terms. We get one term that we've already written down, and we get a term d2 by d theta, d2 by d phi, but that is going to be cancelled by a term that comes from here when this differential operator looks at that. We'll deal with the differentiation of this in a moment. So I'm not going to write down those mixed derivative terms. Otherwise, we've now so that on that understanding, we have dealt with the action of this on that. Now, what about this one? We've got the operation of this on this. We've got the operation of this on this. I've just said that that's cancelled away. What we haven't got is this. When that differential operator meets this, we get the differential of cot is cosec squared, I think. So I think what we have is plus I cosec squared theta of d by d phi. Now the sign should be checked at this point because signs are a pain, right? Well, I think it must be that the derivative is minus cosec squared. Both will be taken afterwards. Right, so that's the derivative of this on this, and then I claim that these brackets are dealt with, and all we have to do is write down the trailing terms here, which is a plus I d by d phi and a minus d2 by d phi squared. Now we need to consolidate our various terms. We have three terms, 1, 2, 3, which are just d by d phi terms, and God be praised, they all add up to nothing because we have a trig identity which is cot squared minus cosec squared is minus 1. So we have that cot squared theta minus cosec squared theta is minus 1. And here's our cot squared. There's our cosec squared, and I'm missing, and this should have had an I. We have an I problem, right? These have to be all, no, I'm not trying to mess with that one. I'm not trying to mess with that. Here, right, I'm going to have a cot squared here with an associated attendant I. I've got a cosec squared with an I, and I have here a 1. So let us by that causes those all to add up to nothing. Then I also can use this identity to consolidate this double derivative and this double derivative. So we have a cot squared and a 1, and I can trade it in for a cosec squared according to that formula there, right? So we end up with minus d2 by d theta squared. It's going to be cot squared minus cot squared, so it's going to be we've got a cot squared and a thing. They both carry minus signs, which means I have to have them on the other side. So we get a minus cosec squared according to this. I'm slightly worried by this. So I'm going to end up with a cosec squared d2 by d phi squared, and I strongly suspect that sign is wrong, but that's what I've honestly got. So that's this dealt with, and this has been dealt with, this has been dealt with, this has been dealt with. I think we're all tickety-boo. We're not, are we? What have I lost? To believe this is the easiest way to do it, it's hard to believe, isn't it? But it is, it is.
The single derivative of d by d theta.
This one?
Yeah.
Right. So that remains cot theta d by d theta, thank you. Right. So we now consolidate this, all being well, into minus 1 over sine theta d by d theta sine theta d by d theta. And this should be, I think, a minus. That sign is wrong. A 1 over sine squared theta. This is how it's usually written. d2 by d phi squared. So I've screwed up on the sign there somehow. So when you differentiate this, we get a cos, which cos of a sine is cot, so that's this term here. We have the double derivative sign, etc., etc., etc. And what is this? This is r squared times the angular part of del squared. And on that note, it's time to leave. We're not quite finished with the calculation, but that's the important bottom line, that L squared is actually with a minus sign, minus r squared times the angular part of del squared. And we'll push that forward into the kinetic energy tomorrow. No, on Wednesday.